Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Today, we're going to be talking about the quantum world, specifically how we think about things changing over time. We're used to seeing things change smoothly and continuously in our everyday world, but in the quantum realm, things are a bit more, jumpy.
It's true. Our intuition about how things change often doesn't apply at the quantum level. That's why physicists have developed different ways of looking at these changes, different frameworks for understanding how quantum systems evolve.
And that leads us to two key concepts, the Schrödinger picture and the Heisenberg picture. It's like having two different cameras pointed at the same dance floor. One camera might focus on the individual dancers, how they move and interact, while the other camera might capture the overall patterns they create as they move together.
That's a great analogy. In the Schrödinger picture, we're focused on the quantum system itself. We're watching how the system's state, its fundamental description, changes over time. Imagine it like watching a single frame of a movie evolve, where the characters and objects within that frame are constantly in motion.
So it's like we're zoomed in on the action, seeing how the details of the scene unfold.
Exactly. And the way this evolution happens is governed by a special equation, the Schrödinger equation. It's like a set of rules that tells us how the system's state will change from one moment to the next. We don't need to delve into the mathematical details here, but what's important is that this equation captures the wave-like nature of quantum systems.
Okay, so the Schrödinger equation is like the choreographer, dictating how the quantum dancers move on the dance floor.
Yes, and it ensures that the total probability of all possible outcomes always adds up to 100%. Even though individual quantum particles behave in unpredictable ways, the overall system evolves in a way that preserves probability. This means that even though we can't say for certain where a particular electron will be at any given moment, we can calculate the probability of finding it in different locations.
That makes sense. So in the Schrödinger picture, the quantum system itself is what's changing, evolving according to this special choreography. What about the Heisenberg picture? How is it different?
In the Heisenberg picture, we shift our perspective. Now, instead of focusing on the evolving quantum system, we imagine the system itself is frozen in time, like a single still image. But what does change is the way we measure the system, the tools we use to observe it.
So it's like we've shifted from watching the dancers to watching the changing lighting on the dance floor. The dancers themselves aren't moving, but the way we see them is constantly changing.
That's a very insightful way to put it. In the Heisenberg picture, we represent these measurement tools, these properties we want to observe as operators, and these operators evolve over time, according to another special equation, the Heisenberg equation of motion.
So while the Schrödinger equation governs the evolution of the quantum system itself, the Heisenberg equation describes the evolution of our measurement tools.
Precisely. And what's fascinating is that even though these two pictures seem very different, they ultimately lead us to the same predictions about the real world. They're just two different ways of looking at the same underlying reality, like two sides of the same quantum coin.
That's incredible. It's like watching the same dance from two different angles. You might notice different details, but you're still watching the same performance. Can we delve into a specific example to see how these pictures work in practice?
Absolutely. Let's consider a simple case. A single particle moving in space.
Okay, so we've got our tiny quantum dancer on the stage. How do the Schrödinger and Heisenberg pictures describe its motion?
In the Schrödinger picture, we'd focus on how the particle's wave function, which describes its position and momentum evolves over time. The Schrödinger equation would tell us how this wave function spreads out or contracts as the particle moves.
So we're watching the particle's wave function, its probability cloud shift and change as it dances across the stage.
Exactly. But in the Heisenberg picture, we take a different approach. Instead of following the wave function, we'd look at how the operators representing the particle's position and momentum change over time.
So instead of watching the dancer itself, we're focusing on how our measurement tools are evolving.
Precisely. Imagine you have two spotlights, one that always points to the particle's position, and another that always points to its momentum. In the Heisenberg picture, we're watching how these spotlights move as the particle dances, even though the dancer itself remains in a fixed pose.
Okay, I think I'm starting to see the difference here. But how do we actually use these pictures to make predictions about the particle's behavior?
That's a great question, and that's what we'll explore in more detail in the next part of our discussion.
Great. I'm looking forward to diving deeper into this.
So we've got these two seemingly different ways of describing how quantum systems change. The Schrödinger picture, where the quantum system evolves, and the Heisenberg picture, where our measurement tools evolve.
Right, and you said that they lead to the same predictions, which seems kind of mind-blowing. How can two such different approaches give us the same answers about the quantum world?
It all comes down to the math. Under the hood, both pictures are based on the same fundamental principles of quantum mechanics. It's like having two different languages that can express the same ideas. The words and grammar might be different, but the underlying meaning remains the same.
So are we basically saying that these two pictures are mathematically equivalent, even if they approach the problem from different angles?
Precisely. And that's why physicists can choose whichever picture is most convenient for a particular problem. Sometimes it's easier to work with the evolving quantum system, and sometimes it's easier to work with evolving measurement tools.
Can you give us an example where one picture might be more useful than the other?
Certainly. Let's go back to our single particle moving in space. Imagine we want to know how the particle's momentum changes as it moves through a magnetic field.
Okay, so our little quantum dancer is now navigating a magnetic force field. How do our two pictures handle this?
In the Schrödinger picture, we'd have to solve the Schrödinger equation, taking into account the effect of the magnetic field on the particle's wave function. This can get pretty complicated mathematically.
So we're trying to figure out how the magnetic field distorts the particle's probability cloud as it moves.
Yes, but in the Heisenberg picture, we can focus directly on the momentum operator. The Heisenberg equation tells us exactly how this operator changes in response to the magnetic field. It gives us a straightforward way to calculate the particle's changing momentum.
So instead of trying to track the shifting probability cloud in the Schrödinger picture, we're directly observing how our momentum spotlight changes in the Heisenberg picture.
Exactly. And in this particular case, the Heisenberg picture gives us a more direct and often simpler path to the answer.
I'm starting to see the elegance here. It's like having different tools in a toolbox. You wouldn't use a hammer to tighten a screw, and you wouldn't use a screwdriver to drive a nail. You'd choose the right tool for the job.
A perfect analogy. And the Schrödinger and Heisenberg pictures are two powerful tools that allow physicists to understand the dynamics of the quantum world from different perspectives. They provide complementary ways of looking at the same underlying reality.
All this talk about pictures and tools makes it seem very abstract. But are there any practical applications of these concepts? Do these theoretical frameworks actually have real-world consequences?
Absolutely. While the Schrödinger and Heisenberg pictures might seem like esoteric theoretical concepts, they form the foundation for many groundbreaking technologies that we rely on today. For instance, understanding the behavior of electrons in materials like semiconductors requires us to apply these very concepts.
So the same ideas that govern how we describe the quantum world are also used to design the chips that power our computers and smartphones.
Precisely. And it doesn't stop there. Lasers, for example, rely on our understanding of how atoms transition between different energy levels. These transitions are governed by the same principles embedded within the Schrödinger and Heisenberg pictures.
Wow, so these seemingly abstract pictures of quantum reality have tangible applications that shape our modern world.
They certainly do. And as we continue to probe deeper into the quantum realm, we're discovering even more applications of these fundamental ideas. Quantum computing, for instance, has the potential to revolutionize fields like medicine materials, science, and artificial intelligence.
It's incredible to think that our exploration of these theoretical frameworks could lead to such profound advancements. It really highlights the power of fundamental research.
Indeed. Every new discovery opens up new avenues of exploration and has the potential to reshape our understanding of the universe.
This has been an amazing journey so far. We've covered a lot of ground, but I have a feeling there's still so much more to uncover. We've talked about how the Schrödinger and Heisenberg pictures describe change in the quantum world, but it makes me wonder, is there something fundamentally different about how change happens at the quantum level compared to our everyday experience?
That's a very deep question, and one that continues to fascinate physicists and philosophers alike. In the quantum realm, change isn't always the smooth, continuous process we're used to seeing in our microscopic world. Sometimes it happens in discrete jumps, like an electron suddenly leaping from one energy level to another.
So instead of a flowing river, it's more like a series of snapshots.
That's a great way to think about it. And these jumps, these quantum leaps, are at the heart of many of the strange and counterintuitive phenomena that make quantum mechanics so intriguing.
It definitely challenges our classical intuition about how things should behave. So we've got these two powerful pictures, the Schrödinger and Heisenberg, each offering a unique lens through which to view quantum change. But are they the only ways to describe how quantum systems evolve? Could there be other pictures, other frameworks out there waiting to be discovered?
That's a fantastic question, and one that's actively being explored by physicists. As we delve deeper into the quantum world, we might find that our current pictures are just approximations, limited in their scope. There might be entirely new ways of conceptualizing quantum change that we haven't even imagined yet.
That's a truly exciting thought. It seems like the more we learn about the quantum world, the more we realize how much more there is to uncover.
Absolutely. The journey of discovery never truly ends. And with each new insight, we gain a deeper appreciation for the profound beauty and complexity of the universe.
Well, I, for one, am eager to see where this journey takes us next. But for now, I think we've given our listeners plenty to ponder about the fascinating ways change unfolds in the quantum realm.
I completely agree. The key takeaway is to always stay curious and never stop questioning. The universe is full of mysteries, and it's through our continued exploration that we unveil its secrets.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.